say in a question or in a textbook, this is an MM1Q, and that would be exactly the same, because remember Kendall's notation for queuing uses letters of the alphabet to describe the way that the services and the arrivals are and the number of servers, and he uses, the system uses N for random arrivals, M for random service time, 1 for one server. So that is a simple queue as well. So MM1Q is a simple queue. Service times and inter-arrival times follow a negative exponential. If the question said it's random arrivals, random service time, whatever, but there's somewhere in there, there's a clue that says we're able to use those formula that I just gave you on that previous sheet. So, to be able to answer, I mean, all those formulae, if you could recall, all had lambda and mu in them. That's all they have, lambda and mu. So all you need are lambda and mu to be able to answer all these questions here. There's nothing else, okay? But this is where some students do get into a little bit of a mess. So we need lambda and we need mu. Now the first thing to say about any formula, of course, that involves two variables, is that the units have got to be consistent. You can't muddle up units. If the arrival, lambda is the arrival rate, number of arrivals in a unit of time. Mu is the service rate, number of arrivals in a unit of time. You can't have the unit of time for the arrivals as minutes and the unit of time for the service as hours, because you can't mix the units. They've got to be minutes, hours. It doesn't matter what you choose actually. If you choose hours, the answers come out in hours. Average time that a customer spends in the queue would come out in hours. If you use minutes, the answer comes out in minutes. So it doesn't matter in a sense, as long as you're consistent and choose something that's the same. Lambda and mu have got to be the same. So it's the first step that's the key, if you like. Getting lambda and mu correct are the key to answering these questions. Now, when we look at the question, of course, we find that the arrivals are given in minutes and the service time is given in hours. So obviously we can't use the information as it's strictly given straight off, because I mean we've got a 3 and we've got a 30 and one's in minutes and one's in hours. But obviously we can convert them. So let's suppose that we take our time limits as hours. So therefore our answers come out in hours and so on. What is the arrival rate number per hour then, from the information given? 30, you say? Is that what you said?
I said
20? 30?
30 per hour.
30. No, right, okay. That's the service rate, 30. We're talking about the arrivals now. The cars arriving randomly. How many arrive per hour?
20.
20, right. Yeah, 1 every 3 minutes on average, in other words 20 per hour is the arrival rate. It's 20 per hour. And obviously the service rate we were given as a number per hour, so that's 30 per hour. Obviously, if you want it in minutes, I mean, it would have to be 1 over 3 per minute, because it's roughly, and that would have to be 1 over 2, per hour. But and therefore, sorry, per minute. And then obviously you can put all those into the formula, but we're dealing then with fractions. It doesn't matter. You just get the answers out in minutes or time or hours or whatever you want to do. But you've got to be consistent. You've got to have 20 per hour, you've got to have 30 per hour. So let's stick with our hours. Then the first question is, what is the probability that a car arriving has to wait? Right? So you arrive at the station, what is the probability that you have to wait? Well, obviously what it is a matter of identifying the formula on this sheet, which is going to be appropriate. And arriving and having to wait, another way of saying that is, or if you want to say put that another way, it's saying that the system is busy. Right? I mean, that is what that is asking. Is the system busy when you arrive? Okay? So that's what that question is saying. Is the system busy? Which of these formulae? Well, traffic intensity is the use being made of the system. So that's telling you how busy or not the system is. So, you know, for part, the first question, part one of that question, the answer is, you know, is going to be A is going to be rho is lambda over mu equals 20 over 30 equals 2/3 or 0.667 or whatever, or 67%. Right. So the answer to the first question is the probability of a car arriving and having to wait is 67% probability, because that's the likelihood that the system is busy and being used at the time.